G'day, in this video we're going to be taking a closer look at reflection, refraction and total internal reflection. So this is going to be the first video which covers inquiry question 4 for module 3. It's all about the properties that can be demonstrated using the ray model of light. So we're going to be applying concepts that we've already looked at in previous sections of this topic, specifically to light waves. So one thing we're going to look at is how images can form in mirrors and lenses using reflection and refraction and applying this idea of the ray model of light. We're also going to be focusing a little bit more closely on quantitative relationships that exist in the areas of refraction and total internal reflection. That's going to require us to apply Snell's law here. And a lot of those quantitative relationships are more explicitly outlined in dot point 6 of this inquiry question. These three formulae here are all going to be covered today. This last one's going to be for our next video and focuses on the concept of the inverse square law. So our key learning intentions today is to review some reflection concepts and apply some quantitative relationships to refraction and total internal reflection. So first off, quick recap of reflection. We have an incident ray and a reflected ray, and we always say that the incident and reflected ray angles are equal to each other. And that's when we're looking at the angle here that occurs in between either the incident ray or the reflected ray and the normal, which is 90 degrees to the surface from which the ray is being reflected off. Important here as well, when we're talking about this idea of the ray model of light, we're focusing on this concept that a light ray travels in one direction completely straight unless there is a reason for the direction for that ray to change. Things like reflection and refraction can achieve that. We also looked at the idea that reflection of light can look quite different on different surfaces. So when we have a nice smooth surface, the normals are pointing essentially 90 degrees up in all directions, which means if we have a series of waves that are all parallel to each other, those rays will all reflect off at the same angle. However, if we have an irregular surface with quite a bumpy pattern, the normals will be pointing in all sorts of directions, leading to dispersed reflection and effectively meaning that you're unable to produce a clear reflected image. This diagram here from the Nelson textbook shows quite well this idea that normals can be pointing in all directions when we have an irregular shaped surface. Something else that we started to look at briefly was the idea that when we have reflection, concave and convex surfaces can lead to light rays being reflected in different directions. For concave mirrors, we see that there is a focal point in which all light concentrates into one particular area. And for convex mirrors, we find that the reflection is going out and diverging in different directions. We also looked at the concept of refraction, which was the idea that waves could slow down as they moved into denser mediums, which also led to changes in directions if the wave was not entering the new medium perpendicular to the line of interface between the two mediums. Here we also briefly talked about the idea that we could have an incident ray and a refracted ray, and that their angles were measured against the normal, which was perpendicular to the line of interface between the two mediums. These three equations in your data sheet are all directly related to refraction and will be unpacked further in this video. We also acknowledged that if we had a light ray which was going from a rarer to denser medium, that the refracted angle would decrease, and then if we were moving from denser to rarer, that the refracted angle would increase. And that could be helped or assisted by describing what happens to a car as it drives from a normal road surface into mud as it changes its velocity, and because one front wheel will be transitioning mediums before the other, it would also lead to a change in angle of the car. Also note that light can be focused or diverged by using lenses which cause refraction. So opposite to how our mirrors work, convex lenses will focus light into a point and concave lenses will disperse that light out. Just for some real life application, the lens of our eye essentially is convex in shape and allows light which is passing into the eye straight on to focus into a point, to focus in onto the retina at the back of the eye. Bear in mind that most of the time when people require glasses due to vision issues, whether they're nearsighted, farsighted, and or have an astigmatism, This is due to an irregular shape of their eye, which is no longer allowing for this perfect shape, which is able to focus light in exactly onto the back of the eye where the retina is, and leading to a different focal point, or in the case of an astigmatism, multiple focal points. To understand the quantitative relationships that we see in refraction, it's important to understand what the idea of a refractive index is. Essentially, it's a value which we give to any type of medium. So let's say this is air and this is water. We might have a refractive index for air N1 and a refractive index for water N2, but it's a value that determines the degree to which light will refract. Essentially, the amount of refraction will be determined by the relative refractive indexes of the two media. The general relationship here is that the less dense media, or the less refractive media, will have a low refractive index, and the more dense media or the more refractive media will have a larger refractive index. Now, the first quantitative concept that we're going to use and apply today is Snell's law. The law states that N1 sine theta 1 is equal to N2 sine theta 2. Essentially, what this is saying is there's a relationship between the refractive indexes of the media and the incident and refracted angles that they produce as a result. So in our practice question for today, we have a ray of light in the air where N is equal to 1, enters a pool where N equals 1.33 at an angle of 21 degrees to the normal of the interface. We're being asked to calculate the refracted angle of the light. The first thing I'm going to do to support the solution for this question is to write out a data column and draw a diagram to demonstrate the refraction of the ray of light as it passes into the water. Note too, as a general rule, when using these formula like Snell's law or the other formula for refraction that are included in your data sheet, anytime you see something notated with 1, so N1 or theta 1, generally we're referring to the incident ray. And if you see N2 or theta 2, we are referring to the refracted ray. So for our solution, I'm going to rearrange our Snell's law equation for theta 2, as this is the variable which we do not know. From here, we need to substitute, and our final answer should be correct to two significant figures, given the angle that we were provided with in the question. Our final answer there is 16 degrees. This does make sense. Our angle should be smaller for theta 2 because we are transitioning from a less dense medium to a more dense medium, or from a lower refractive index to a higher one. This next equation that we have helps to describe where we actually get this refractive index from. Essentially, N is our refractive index. C is the speed of light. Technically, this is in a vacuum. We can also consider the speed of light in air to approximately be the same. In your data sheet, it's given as 3.00 times 10 to the 8. It would generally be accepted to assume that the speed of light in Earth's atmosphere is equivalent to the speed of light in a vacuum to those three significant figures. The last term here, Vx, is going to be the speed of light in medium X. So for example, if Nx was a refractive index for a piece of glass, Vx would be the speed at which light travels through that glass. We can use this equation either to calculate for the refractive index of a particular medium, or use a refractive index of a medium to be able to calculate for the speed of light in that medium. I'm going to demonstrate both of those concepts in questions A and B. Now for question A, we're being asked to calculate Nx, the refractive index of a plastic container, if light travels through it at 2.05 times 10 to the 8 meters per second. So to solve, what I'm going to do is write up a data column, identify and rearrange my equation if I need to, and then substitute to solve. And there you go, our answer for question A. The refractive index for the plastic container is 1.46. Now for question B, we're being asked to calculate the speed of light for a ray which is propagating through water, assuming that the refractive index is 1.33. So again, pretty much the same process. I'm going to drop a data column, identify my equation, rearrange the equation if I need to, substitute and solve. And then we go, the velocity of the light ray in water is going to be 2.26 times 10 to the 8 meters per second. Note that for my answer, both for part A and B, I've given my answer to 3 significant figures, given that all values used, either given or from the data sheet, are given to 3 significant figures as well. Finally, today we're going to show some quantitative relationships for total internal reflection. Previously, we've looked at the idea that if we have a ray of light which is traveling through a medium which has a higher refractive index, we're going to have a refracted ray angle which is larger than the incident ray angle. Essentially, what that means is you can keep increasing the incident rate until we hit what we call the critical angle. And this angle is where the refracted ray is equal to 90 degrees to the normal. Once we increase the incident ray any further than that, we observe a phenomenon called total internal reflection, in which the ray will no longer exit the medium of a higher refractive index, but instead reflect back into that medium with a higher refractive index. Today we're going to unpack the formula which allows us to calculate the critical angle for total internal reflection. Now we have this formula, sine C is equal to N2 over N1. Again, just keep in mind, N1 is referring to the first medium that the light is in, essentially the medium where the incident ray is, and N2 refers to the medium where the ray will exit and refract. Before I actually tackle the question, I'm going to show you how we get this formula from Snell's law. So to do that, I'll need to draw up a little bit of a diagram first, and then I'll show you the link between Snell's law and this equation. So in this little proof, we're assuming that we've got a light ray at the critical angle, and that's theta c. Essentially, at this critical angle, we have a refracted light ray, which is at an angle of 90 degrees to the normal. If Snell's law states that n1 sine theta 1 is equal to n2 sine theta 2, and we assume that theta 1 is going to be theta c, this critical angle, and theta 2 is going to be 90 degrees, well, the first thing that we can say is that for sine theta 2, sine 90 is going to be equal to 1. Therefore, that is going to mean that on the right-hand side of the Snell's law equation, n2 sine theta 2 is just going to become n2. And that's what I have then drawn up on the right, that if we have n1 sine theta c instead of sine theta 1 being equal to n2, then we can rearrange the equation for sine theta c, and that's going to be equal to n2 over n1. And that is our critical angle equation that we see in our data sheet. Now we can apply this to be able to calculate for the critical angle for light. All we would need to know are the refractive indexes of the two medium. In this case, we've been told that we're passing from glass, where n is equal to 1.72, into air. Now, keep in mind, if you're not being told the refractive index for air, it's very safe to assume that the refractive index is going to be equal to 1.00. So to solve for this, all I'm going to do is draw up a bit of a data column, a diagram, and then I will substitute into our equation. Now, final answer here, the critical angle will be 35.5 degrees, meaning that if we were to increase the incident angle beyond this number, we would start to observe total internal reflection. Thank you very much. In the next video, we'll finish off our inquiry question based on light. We'll look a little bit deeper into the concept of the dispersion of light, as well as the inverse square law. Catch you in the next video.